Thanks a lot, Simon. So I hope the sound is good with you. Okay. So indeed, this session is still part of the workshop that we organize to really give the basics for image processing. And today it's about image classification and segmentation. So I will give some, I would say, introduction to this topic, and then you will have a more in-depth talk in the two following talks. So maybe just to give some maybe background also about the ANERIS project. So there is a lot of things happening in ANERIS, and they are all aiming in developing what is called operational marine biology. But here, what we are involved in, and which is basically the idea about this workshop, is one particular technology that we aim to develop, like taking underwater images that could come also from a citizen at some point, and using what was presented in workshop 2, so image restoration, in order to detect and identify the different species for a lot of different applications, like watching biodiversity, but there is also economical applications. So before starting also, I just point you to this nice survey results that was just out like about 1 month ago in Nature, and that was a survey reaching out 1,600 researchers, and basically you can have a look to it. It's kind of interesting, and something which was reporting also, it's which are the barriers to progress. And the barrier to progress, I mean, it's dependent of the two categories of people that answer the survey. So the one who study artificial intelligence and the one who use artificial intelligence. And I guess most of us here, we are part of these people using artificial intelligence in research. This is not, we are not doing research in artificial intelligence. We are answering other questions using artificial intelligence. And it's mostly training and skills which are considered missing. And this kind of workshop today, I mean, and there is plenty of other one, it shows also that the community is organizing itself in order to provide more of these resources for this. So I will start again with the definition you already heard during the first two sessions of the workshops, but it's the morning, we're warming up. But so what is artificial intelligence? So basically, there is plenty of definition. I took the one from IBM, but basically it's really using computer science and data set in order to solve problems that you will do normally as a human, but letting the computer solving the problem for you, so taking a decision maybe for you. And inside artificial intelligence, we do most of the people working with computer are doing artificial intelligence. And then inside this big field, there is machine learning and there is deep learning. And because we are talking today about image classification and segmentation, I will just re-explain the basis for this and what are the differences between these three approaches based on a segmentation example. So just some vocabulary. It may be obvious for some of you, but it's just that everyone is at the same stage when we start this session. So basically, there is roughly two main tasks that you can do with a computer. I would say one is classification and the other one is prediction or regression. So what is classification? Basically, classification, you have data, and the data are labeled with a class, such that yes or no. And the purpose of classification is to find an algorithm then that will separate the class yes from the class no, if you do a binary classification. And then the output and what you want to get is this model that will represent this algorithm, separating your two classes. Prediction or regression is another kind of task. Basically, you have data with an input X and an output Y, for example, and what you want to achieve is the relationship between X and Y. And that will give you a model allowing you to predict for any new X what would be the value of Y. So also for the vocabulary, basically in these two examples, you have the notion of features. So here, in that particular classification scheme, I call X one feature and Y another feature, basically, but that's these features that will allow to discriminate between the two classes. And then the output of the algorithm is yes or no, the class. If you do prediction, so basically you may have one feature, X, and Y here in this graph was actually the output. Okay, so I'm going to exemplify the difference between what we call ad hoc artificial intelligence and machine learning, like shallow machine learning, and what is now called deep learning. So I'm starting for a task from biology. Okay, I will show other examples and from the underwater marine world, but here this is an image taken from a fluorescence microscope in 2D, where you can see cells with different channels, each one measuring the expression of a different protein, and some will enhance what is called nuclei or the cells. And here, for example, the task would be to measure the distribution of size of areas of the cells. So, and the purpose in order to do that will be to identify any cells individually. So the first thing you would do in an ad hoc method is, okay, basically looking at your image and say, okay, which information do I need to identify cells? And the information to identify cells here would be contained in this, this image. Then this is a typical workflow. So workflow is a pipeline that we will use to process an image in order to get the segmentation at the end that will allow us to compute the size of every independent object. And the very classical way to do so is basically filter your image. And I'm going to come back to filters because this is also super important for machine learning and deep learning. Then you will identify the two classes in the image, do some post-processing, and then identify each object. So here, for example, the post-processing is very simple. We are just blurring the image just to remove this tiny pixel at the end. So how does it work? And I'm just spending a few minutes to explain, because once again, that's the very basis of everything you will do also in computer vision, but in deep learning also. So basically, what we are going to do is applying a filter, and applying a filter is working like this. So an image, as you know, is a matrix, okay? So you have values, and here you can see there is a black point, which is a low value here surrounding by higher value. Here you have an higher value with black wand. And when I apply a filter, here I will define a kernel. So I will human engineer a kernel. So this kernel here is composed by exactly the same value every time. And what it's going to apply when you apply a filter, it's basically what is called a convolution. And convolution is a kind of simple mathematical operation where you will actually take your kernel and multiply every case of your kernel by the matching one. So here it would be 0 dot the value of the kernel, 1 multiplied by the value of the kernel, etc. And at the end, you get a value. And if you observe what was my kernel, basically it was always the same value. So what you did here was just multiplying by 0.11, which is actually 1 over 9. You had 9 case considered, and this is exactly an average value that you did compute. Okay, and then you do that, you will obtain a new value. That would be the average value for this particular area, and that will replace this value in the new image. And you do that for every pixel in the image until you obtain a new image with filtered value. You can do that with different scale. If I come back with my average filter, my mean filter here, with a kernel size that would be the size of the image, then the result would be the mean intensity of the image. So here, the important message is that basically you can change the filter kernel, but you can also change the scale, and the scale is giving different information, and you can even embed information about neighborhoods or spatial relationship in a filter then. There is plenty of other filters. I will announce other things, like the well-known filter is Laplacian of Gaussian, with 2S, sorry, called also Mexican hat, and which is basically using this kind of kernel. And if you think about it, not from the mathematical way, but basically if you do a convolution from this image to another image, convolution is very similar mathematically to a correlation. So basically it will enhance then and give a very high answer where there is spots, because this is a spot. And you can design and human design more complex filters. So for example, here, this is a filter that will adapt to the content of the image. So the kernel will change according to the content of the image. And this is, for example, super useful to detect like filaments. So from this to this is not deep learning, whatever, it's just a filter that was human engineered in order to get from here to here. Okay, so here it was a very simple filter. Then you do something very classical, which is the most classical way of separating background from object of interest, which is called thresholding. Basically, you choose a value on the histogram of the image, separating low value pixels to high value, assuming that pixel of interest have a higher value. And then you do some post-processing and identify objects. And here you also can add human-defined rules, such as, okay, a cell cannot be smaller than a certain amount of pixels, for example. When you go for machine learning and segmentation in machine learning, this time, so you also start from your images, but this time you are not going to design specifically for your task the filters you're going to use. What you will use is a bank of filters that was predefined also by humans, but some humans predefine them for you. So you have a lot of different filters, and every filter, they have different scales, so they will give some different information, different kind of object will be enhanced in the image by the filter, and you get like this hundreds of different filters applied to your image, whatever you want to do. And then where the learning part is because you will indicate to the computer example of what you want and what you don't want. So for example, here I want myself, so here I have a yellow. So I indicate some pixels here, and here I indicate some pixel from the background, okay? And what would happen in machine learning, basically, you will go to a kind of hyperspace dimension thing that here I will simplify using only 2 filters. So that will be called features, okay? So imagine I had only 2 features. So every pixel that I gave as an example here has one value in one filter and another value in the other filter. And then you got the representation in this simplified 2-dimensional space. In reality, once again, there is hundreds of different values. And then what will be, now comes the real learning, and the learning is basically constructing what's called a classifier. And the classifier is basically finding the domain separation in this hyperdimensional space, such that your example pixels and of background and of object of interest are separated. So that will be the white line here is basically the classifier, the domain definition. And then for any new other pixel of your image or in other new images, you will basically just apply the label to the pixel according to the position in this hyperspace. And then you get a first proposition that you can we train because here it was not good. So you will give another example of this is not a cell. These cells should be separated, for example, and we train like that and find another classifier. So what is happening in deep learning? So there have been introduction and a lot of example in the two first workshops, but here I'm just coming back to the most classical one, which is the convolutional network. And here it's a particular example of UNet, which is one of these convolutional network. And here, basically, this time, you don't predefine any features. And every little layer here is actually containing what would become kind of filters and the purpose and the parameters that would be estimated. So in part of them would be actually the weight of the different filters inside that. So it will design for you the features that you want to extract in order to get the result. So here you will need to give as an input what you want to start with and train it using the output, the full output that you want to get. And there is then millions of parameters to be set, okay, every weight of the different filters, but also there is a lot of other hyperparameters to be set, even for one fixed architecture. So it means that you need a lot of data. If you remember high school again, when you have an equation with a lot of unknown, you need at least as much data as unknown. Okay, so basically deep learning is somewhat a paradigm change. You have heard that a lot during the previous session as well. And usually what we do when we do computer vision or any other kind of problem, so we have some input data and then we design a program that will mean like some rules, some way to obtain your output data. In deep learning, basically you start with some input data and expected output data. And what you will design is a model. Then, of course, the model, you can come back to the normal way of applying it, inferring it, like then you will be able to apply it to any new input data, which is the purpose at the end. Okay, so when you do classification, for example, you have different kind of tasks that you may want to achieve. So one very common is what is called image classification. So you don't segment anything, you don't localize anything. It's just you give patch of your images and you say what is inside. So here, for example, mitotic cells or non-mitotic cells. You can do also object classification. So if you have some objects segmented, you can extract features like maybe human engineered features. And from these features, you can actually classify the object as you were classifying the image patches. Here you classify the object types. You can do what is called semantic segmentation. Semantic segmentation is classifying pixels in different classes. So here it's binary semantic classification segmentation, but you can have more than 2 classes. And you can do what is called instance segmentation, and in that time you want to identify a unique object. They can be from the same class or not. I mean, that's another question, but at least you are able to define well-delimited object and saying it's not the same object. Then what you have seen, and that was the purpose of the previous session also on image restoration. Just in the example before, I was doing classification, and we have seen prediction was mostly used for image restoration. So basically, you have seen that you can get denoising from it. You can also get what is called like image translation and predict another modality. So going from one image, you can go to another type of image, for example. Here is another example where you can just predict what would be another modality from an easier to get modality. Okay, and this is exactly the same task that you will get like when you're looking at underwater images. So you can go image classification, so saying there is fish, or maybe even which species of fish are here, but without localizing them. You can localize and maybe classify this region of interest containing fish. You can do semantic segmentation, so just fish, no fish in the background, or instant segmentation, where you have identified and separated the different objects here, fishes. Okay. For this, most of the time, if you want to use deep learning, you need data sets, and you need data set with ground truth or annotation. So depending on the kind of task that you want to do, you will use different kind of annotations. You can use some pixel examples. You can do full mask also of the object that you want to separate. Same thing here, you would need labels if you want to separate different objects, and if you want to do denoising, for example, you need some reference good data set. And then you will maybe train your data on the data set you gathered, but you also need to train with much more data, because you will get during the training a very good model getting and fitting very nicely your data set, but it will maybe not work that much if you add another and if you test it on another data set. So basically, that's why usually you separate your data in training and validation data set. And either like this, you need also maybe to test it in order to estimate the performance of your network on a data set which was never seen, which is called the test data set. And this is why you need to spend a lot of time also designing and organizing your data in order to do, for example, cross-validation with your data. So before going to this very heavy slide, here the message is that when you use deep learning, for example, it's up to you to choose where you want to use it. And there is plenty of solution of where you want to use it. And here I'm going to take a simple example, once again from biology, where here the purpose is to help clinicians, I would say, with a diagnostic of a certain disease. And here you can see this is coming from what is called peripheral blood smears, coming from patient, and you have different type of cells, okay? And maybe if you are not used, you cannot see the difference, but cytologists, they can see the difference between these 4 types of cells. And what define, based on the experience of this hospital biologist, what defines the different kind of disease they are interested in is the numbers and the relative proportion of these cells. So you can see there is 4 types of cells, and according to the proportion, some of them, okay, they are doing well, the orange one, and this is another kind of disease, and this is vexas, this is what I'm interested in. So when you want to solve a task like this, okay, basically saying if the patient has vexas in that case, for example, or not, what you would design is some kind of a workflow, even if you're using deep learning, saying how you will achieve your result. And the result here, for example, would be the diagnostic of the patient. First example, you get the source images. You can decide to apply ad hoc method or a classical segmentation method to find your cells, on because this is basically not that complicated to identify this kind of cells. Okay, so you will get sub-images of your cells, and then you can define features by yourself. And features can be something that can be expressed, I would say, in human words. So, for example, the granulosity, the shape, the ratio between the cytoplasm and the nuclei, all these things, you can express them as numbers. And based on these numbers, you can decide that, okay, if the cell is answering this and this and this features, then it means that it is this type of cell, otherwise that will be another one. And based on that, here also you can either use your human-defined algorithm, as a reminder, for example, based on the proportion of cells, or even maybe some deep learning based classifier in order to decide if the patient is which diagnostic it has. Then you could have used deep learning at another step. So for example, you can just use some localization algorithm detection of cells, and then don't try to get the mask or do any measure, and then use CNN in order to extract features from these different images that will give you as an output the same thing as here. Or you can even give the image, let the deep neural network do the job for you of identifying the object and everything, and do the classification. And you can also directly say, okay, I give my image and my output would be Vexas, not Vexas, whatever. So then the main difference also, okay, would be maybe the level of performance, but also maybe the explainability of what you're doing and the how much human in the loop you want in this kind of approaches. So it's really important to think about what would be your strategy, because there is plenty of strategy to answer the same question. So now if I come back to the ANERIS project, which is more about underwater imaging. So one of our purpose basically is to get images from some observational devices, such as the one which was presented by Alex from Oslo Met in the second session, or maybe once again using images taken by amateur divers, whatever. And then we have seen there is a lot of very impressive work regarding image restoration that was done and presented by our colleague from Israel. And then here the idea is based on this image to identify automatically where there is species and everything. And here, once again, it's a strategical choice. So do we want to just identify which species it is? Or also what we can do is involving citizens, and I will come back to that and how they can be involved, and in order to also validate maybe what was proposed or validate the classification. So just to give a little bit of fancy network that are developed now and that are working very nicely. So for example, I don't know if you heard, so in April, there was this paper describing the model, which was already released before, but a segment anything model from Meta AI, and which is like, the name is indicating a segment anything model, meaning it's a foundation model, meaning that it was being trained on millions of data sets for anything. And its purpose is to do instance segmentation from what is called prompt. So it's very similar to natural language processing or ChatGPT stuff in the principle. And basically it has some encoding of the image and embedding of the image in the kind of characteristic features, generic features of image, and then it does the same with the prompt, and then it gives you what would be a mask. So here I process the unrestored image, and as a prompt, you can use basically prompts everywhere. Okay, you don't know what you want to segment, and if you use prompts everywhere, that's the output directly, and you can see that the little maybe shrink, I'm not sure what is it exactly. Here, it's not well separated from this. If you do impose some prompt on some ROI focusing on these two different species, then even with this low quality image, this segment anything model will be able to separate the two objects. If you use restoration, then it's much more simple. So that's also demonstrating the importance of segmentation. Even if you could train again your model, if you have tools to obtain that and getting the task easier, so why not using it? And from here, for example, using the same strategy of putting font prompt everywhere, you will get directly these two nicely masked. Once again, without any retraining, it's just the generic model that was used here. And this kind of models now, they are very accessible. I mean, you got the code, you can run it if you want from a Google Colab, whatever, and it's all open source, and you can redo that. So as it was mentioned, there is a few, not a few, there is kind of a lot of database, but what I want to announce here is that what you want to achieve, if you want to classify species, and if I here look at the Minka database that was developed in part also by Raume Pierra, which is only observations from the Spanish coast, I don't remember which one. And here on this, you can see that there is already about 6,500 species, okay, and a lot of annotation that will be annotated at the level of the image. And here I'm getting one particular fish, which is called Oblada melanura, that you can see here with a very low quality image, and here at the middle of other kind of fishes. So we have plenty of model, which is actually very nice and impressive with the segment anything. Once again, without any training, at least you can get the mask of the fish, so you can then maybe extract features, whatever, to identify further the fish. And even in very low condition, you can see it's getting the fish quite nicely. And yes. Now, so that's when I put on, then here you will get a mask that will maybe serve to detect an ROI, so from which you can extract features, but you don't get any classification. Another famous network in deep learning is called YOLO. So YOLO is actually not really using classification. It's more doing the object detection and the classification part, but is doing it using a prediction framework. Okay, it's a little bit different from using a classification framework, and basically what it does is basically trying to fit a bounding box and predict a value from a set of from a predefined grid. And here there have been in the marine biology community a lot of effort, and there is, for example, a big database which is also proposing a model zoo, which is called PhantomNet, and they train the version 5 of YOLO, and we are now at version 8, I believe. I can check recently, but last time it was version 8. And basically here train on 691 species of fishes, okay, from 33,000 images. They were able to get very nice results on the classification. Once again, because it's a pre-trained model, it's super simple to use. Everyone can use it. You download the model, which is called .pt, and you just replace the weight in the YOLO v5 Google Colab, for example. You can get easily on the net, and you just replace it and you run it on the new images. And if you try it, for example, you say, okay, that's great, problem solved. And then if you use it on other images, I don't know how many of you are marine biologists or knows about fishes, but basically this is completely wrong. So that will be the detection. So detection are nice, huh? Not all of them, but some of them are nice, but the classification and the prediction is not that good, and still it has some kind of a high confidence probability, but it's completely wrong, because it's not malicious products. And here, Bactiraja coinciding is basically some kind of flat fish, so I have no idea why you consider it was that. And here there were no detection at all, for example. You could not see because it's not so good. Oh, sorry, there is some microphone here. YOLO is not so good for a small object detection. Of course, if you test it on the of the data set himself, that's working perfectly. So here it's what is called a malicious productus, and that you can see here. And if it's on trained image, that's very good. And also what I didn't say is that this image, they come from a different database, okay? And they're actually showing species that were not in the 691 species listed. So of course, he cannot guess what it was, but he cannot also guess it was not that. I see you get a similar score here. And yes, so this was this. So basically, that's also asking the question of the features that are used, because apparently the color is not. So yes. And yes, that's working nice with a lot of different images, but then you cannot be 100% confident in the kind of classification because here, okay, that's a quab, it's true, but it's clearly not the same quab as this one, and they were classified the same. Okay, so there is plenty of underwater image database, and there is here I'm not talking at all about plankton. I'm just thinking about what's called a more benthic or macro species images, and you will know more about plankton during the last talk about on ecotaxa. But I'm just listing that, and all the slides would be made available on the Zenodo of ANERIS. So I'm not detailing, but basically you have data with some ground truths aiming at different tasks, such as image recognition and detection, or image enhancement, or maybe detection or classification, and this is just a few examples of what is available. And the thing is that the number of classes is just gigantic. I don't think we have the equivalent in biology then. And that's why the task definition is important, because here you've seen there were plenty of fishes.
I can't hear you. I'm listening to talk. What are you saying?
Inside the sorry. We had plenty of we had plenty of different class just for fishes, but there is much more than fishes under the ocean, and that's why one of the possible approach is also one which was taken by another project I'm just going to talk about in 1 second. I just want to mention that there is also plenty of databases available and with contours in the biological microscopic domain. So there is some list of these data sets that you can find with some reference. And here, what I wanted to mention is that how can you make sure and maybe get input from people? And that's something which has been implemented in other projects, but basically it's very similar to what the Google image search is doing. So for example, if you give this image to Google Image, it will return you, okay, other kind of image, and I'm not a fish specialist at all. And okay, I can guess, yes, it looks like it may be indeed Dictonactus mormirus, or le marbré de Rennes marbré in French. So it looks okay. So maybe I can confirm the classification that will be processed from that. Same thing, for example, if I am able to give this a small ROI here, then I can compare with other images we could have in the database. So here clearly it's not a myriapod, okay, for sure, because myriapods doesn't look to live underwater, so I will not classify this as a myriapod, maybe more like a crab stuff. And this is what is used then in PlantNet, and what is interesting also, and once again, it comes with your full workflow of designing what you want to do, is maybe you can use this kind of image similarities, and in order to help with the classification, and refine the classification, and add more species also, and continuously training your network. So just to conclude, before taking any question, if time allows, but basically it happens that in deep learning, computer vision, and in particular classification and segmentation is one of the most active field, and a lot of major actors such as Google, Facebook, whatever, have been putting a lot of means. For example, the segment anything model, I say they gathered millions of data, annotated them, train of, I don't remember, but I guess it was 256 high-end, high-level GPU cards during several days, whatever. So that means that we may not have. And even in deep learning is not magical. I doesn't mean like you give a task and he will do the task for you. It's your job still to define what you want to do exactly, what is the task, what would be the different part of your workflow. You're still using workflow with deep learning. And you need some understanding about how it's working and why it will maybe not work from time to time. For example, if you have never seen a class, there is no way you will recognize your class. You may have limited data set, and I didn't have time to tackle that, but there is a lot of strategy now to work with limited data sets. Don't forget about image enhancing because it may simplify the problem. I try to show that on the segment anything using tally restoration here. And there is also a lot of other questions that really depends on the fields you are processing. So for example, in particular, when you're dealing with marine biology, so you have a lot of hardware problem. And the question is, where would you do the processing and how do you transmit the image? What do you store? Whatever. So that may be tackled in the next talks as well. And that also means that you need not only to have super good network workflows trained, but they also need maybe to be low power and they need to be high speed also. And with that, I will stop and acknowledging the different partners of ANERIS and some other partners from other projects locally that which are contributing to